Swayam Prabha. Digital India. Educated India.
Hello and welcome to today's class. We will begin by having a brief recap of what was covered in the previous class. So, one of the most important concepts we had introduced in last class was the concept of expectation, okay, and variance and covariance. Okay. So, expectation is written as E of x for a random variable x, okay, and is defined as either summation x p of x over all x for discrete RVs and for continuous RVs. Okay. So, let us take the following example. Okay. Let us say f x, the probability density function f x is defined as follows. Okay. So, you have defined the probability density function f x of a random variable as a plus b x square for 0 less equal to x less equal to 1 and 0 otherwise. Now, if for this random variable you are given E of x is equal to 3 by 5, then what is the value of a and what is the value of b? Okay. So, we essentially have two unknowns in this problem, a and b, and we are given this condition E of x equal to 3 by 5. Okay. So, how do we go about it? So, of course, since f x is a probability density function, we know that minus infinity to infinity f x dx is equal to 1. This gives us this one equation. So, if we go through it, this implies okay. So, this is equation 1. Okay. So, I can write a plus b by 3 equal to 1. Okay. Now, the other equation we have is E of x is equal to 3 by 5. So, E of x is defined as x f x dx. This is 3 by 5. Okay. So, this will boil down to x okay. So, this will be a by 2 plus b by 4 x square by 2 is equal to 3 by 5, implying 2a plus b is equal to 12 by 5. Okay. If 2a plus b is 12 by 5, then okay, this is equation 2. So, from this equation I can write b is equal to 12 by 5 minus 2a, implying b by 3 equal to 4 by 5 minus 2a by 3, and if we plug this value in equation 1, then we have a plus 4 by 5 minus 2a by 3 equal to 1, implying a by 3 equal to 1 by 5, a is 3 by 5. Okay. So, then b becomes 6 by 5. Okay. So, thus f x becomes 3 by 5 plus 6 by 5 into x square. Okay. So, we also have the following variations of expectation. So, we know that E of a x plus b can be written as a exponential of x plus b. Okay. Now, let us say we have a random variable, okay, such that e of x is 2, e of x square is 8. So, we want to find out e of 2 plus 4x whole square. Okay. What would be the expectation of this particular variable? So, what is it? I can expand this equation, expectation of 4 16x plus 16x square. Okay. Then I can write expectation of 4 plus expectation of 16x plus expectation of 16x square. Okay. So, here in this equation I have invoked e of x1 plus x2 plus dot dot xn is equal to summation e of xi. Okay. So, now e of 4 is a constant, it will be 4. I can take 16 out. So, I can make use of this expression. So, it is 16 expectation of x. I can take expectation 16 out here also, and I get expectation of x square. Okay. So, 4 plus 16 into expectation of x is 2 plus 16 into 8. Okay. So, is 4 plus 16 into 10 to 164. Okay. So, I can make use of this and the identity e of summation of xi is equal to summation e of xi, okay, or I can break it down. Okay. I also have the following thing. If you have a function e of gx, so actually this we broke it down, but this is more like e of gx, okay, is summation of gx px dx, okay, or integral gx fx dx. Okay. So, we had earlier determined, so if I do e of x minus c whole square, I can expand this as e of x minus mu plus mu minus c, okay, whole square, and this we had shown that this is greater or equal to e of x minus mu whole square. So, this is why mu is the best predictor. Okay. Of a RV. Okay. So, this will give you the best value of expectation, it minimizes this. So, e of x minus mu whole square is nothing but the variance of x. Okay. So, I can expand this So, variance of x has this identity. Okay. Now, while so I have this, I already showed that e ax plus b is equal to a e of x plus b. Okay. So, what do we get for variance of ax plus b? So, what we found was, I do not need to derive this equation, but what we found was variance of ax plus b is nothing but a square variance of x. Variance of a constant is 0, okay, and when you have a prefactor scalar multiple, it just takes the square form. Okay. So, when you have multiple independent random variables, x as defined as x1 plus x2 plus dot dot xn. So, you can write e of x is equal to summation of e of xi. Okay. However, you cannot write variance of x1 plus x2 plus dot dot dot. You cannot write equal to variance of summation variance of xi you cannot write. Okay. Let us see why. So, imagine I have variance of x plus x, right. So, if I use this particular formula I should get, so equal to, this is variance of 2x should return me a value of 2 variance of x. However, variance of 2x, if I use this formula, so variance of 2x, 2 square variance of x. Okay. So, this and this are not the same. Okay. So, you cannot write this equation in the general case. Okay. Variance of x summation is not the summation of the variances. Okay. However, so in the general case I am not going to derive this equation. You can write variance of summation of xi is given by summation variance of xi plus this is over I, this is over j, and this expression has to be computed for I not equal to j. Okay. So, this is the general case. So, if I have two variables, I can write x1 plus x2 becomes variance of x1 plus variance of x2 plus twice covariance of x1 comma x2. Okay. You have 2 of covariance of x1 comma x2. How do we define covariance? So, covariance of xi comma xj, or let us say covariance of xy, is defined as expectation okay. So, I can expand this okay. I can write this as E of xy minus mu y E of x minus mu x E of y plus okay. So, E of x is mu x and E of y is mu y. So, this nothing becomes nothing but xy minus 2 mu y mu x plus mu x mu y. So, this finally you can write it as E of xy minus mu x into mu y equal to E of xy minus Ex into E of y. Okay. So, this is your definition of covariance of x comma y. Now, what you see is if x and y were independent, so if x and y are independent, then covariance of x comma y is equal to Ex into Ey. So, I can expand Exy as Ex into Ey minus Ex into Ey. This gives me a value of 0. Okay. So, for independent variables only, I can write okay. So, this equation is applicable when your random variables are independent of each other. Okay. So, in general this equation is not valid, but when the random variables are independent, then you can write this equation. Okay. So, let us solve two sample cases where I can use this equation. Okay. So, imagine you are taking a coin toss case. Okay. You have toss of a coin. Okay. And you are tossing it 10 times. Okay. So, you want to know you want to compute variance of number of heads. So, 10 times of heads resulting from 10 independent coin tosses. Okay. So, what you see here are independent coin tosses, right. So, I can write variance of summation xi I equal to 1 to 10 as nothing but summation I equal to 1 to 10 variance of xi. Okay. So, covariance is 0 because the events are independent of each other. Now, let us take a single coin toss. Okay. Okay. So, I can write xi if head, 0 if tail, right. So, in this case my E of xi becomes 1 into probability of 1 which is head, which is half, plus 0 into probability of tail, which is half. So, this is simply half. I can write E of xi square also, okay, which is 1 square into half plus 0 square into half, simply half. Okay. So, my variance of xi is E of xi square minus exi whole square equal to half minus half square equal to 1/4. Okay. So, thus my variance this becomes 10 into 1/4 is equal to 5/2. Okay. So, let us take another example. Okay. You take the example of roll of a die. Okay. And in this case again let us say 10 independent rolls of the die, okay, and you want to know what is the variance of the sum obtained from 10 independent rolls. Okay. So, as in the previous case we can again have the same thing, summation xi is summation variance of xi. Okay. So, this would give me, so I want to compute variance of xi, right. So, for rolling of a die, right, for rolling of a die, you know we had the previous case we calculated E of x is equal to 1 into 1/6 plus 2 into 1/6 plus 6 into 1/6, okay, and this will come to be, okay. So, 1 plus 2 plus 3 plus 4 plus 5 plus 6 by 6, which is equal to 7 plus 7, 14 plus 7, 21/6, 7/2, okay, and E of xi square, E of x square is equal to 1 square into 1/6 plus 2 square into 1/6. Okay. Okay. So, finally, you will see variance of xi. So, I can write this as xi. Okay. Variance of xi will come to be, so you can compute this value and see, I think it will come to around 35/12 or something, but just check. Okay. So, if this is for a single variable, then I have to multiply. So, variance of summation xi then becomes 10 into 35/12. Okay. So, the correlation coefficient rho is given by nothing but covariance of x comma y by root of var of x into var of y. Okay. So, you can see how you can make use of expectation and variance for calculating various quantities and use this to estimate the variance of a population depending on the events. So, two important things from take away from this class: you use this general expression E of g x is nothing but summation g x p x t x, summation p or integral, okay, g x f x d x. This is one thing to remember. You can write E of summation x I as summation E of xi. Okay. You can write variance of Ax plus b is a square variance of x plus b. Okay. For independent, okay, or v's, you can have variance of summation xi is equal to summation variance of xi. Okay. But in the general case, so you have to have variance of summation of xi is summation of var xi plus okay. So with that, I thank you for your attention, and we will meet again in next class.